Hello everyone, we are Group 37 from January 2022 semester and we are presenting our integrated design project on the SMR technology. In this presentation, we will cover on 3 courses which are CEB 2043 Reaction Engineering 1, CEB 2053 Process Modeling and Simulation and CEB 2063 Separation Process 2. Hello everyone, my name is Umi Hazra and I will be presenting for CEB 2043 Reaction Engineering 1. Hydrogen is considered as an excellent alternative to fuel due to its capability to drive the generation of electricity without emitting harmful pollutants. Hydrogen have a high potential to be a carrier of energy for electricity, power generation and vehicular use. Among the methods used to produce hydrogen, steam methane reforming or SMR is the most established and generally used process to produce hydrogen in a large scale. In both SMR and WGS process, the reactor used is the packed bed reactor of PBR because it has a high conversion per unit mass of catalyst, continuous operation, low operating cost and it is simple, flexible and easy to scale up. For SMR, the catalyst used is nickel oxide which is promoted by aluminum oxide. Nickel oxide is used in it has high reactivity and catalytic activity as well as low attrition and nickel can be used in low percentage. Nickel oxide can withstand high temperature and it demonstrates good chemical strength. Meanwhile for WGS, iron oxide is used as catalyst and is promoted by chromium oxide. Iron oxide is active at temperature within the range of 350 to 550 degrees Celsius and doping with chromium oxide will prevent sintering of iron oxide crystals. And the characteristic surface of iron oxide possess acid-base properties and oxidation reduction potential. This is the process flow diagram for the steam methane reforming reaction. First, the feed stream will pass through a mixer in order to combine both streams of steam and methane gas. Next, the mixture will be introduced to the SMR reactor where methane and steam is reacted at temperature of 700 degrees Celsius and pressure of 25 ppm. In this reaction, carbon monoxide and hydrogen is produced and the reaction is endothermic. Next, the mixture will pass through a condenser since WGS reaction will take place at a lower temperature compared to the SMR reaction. Hence, condenser is used to reduce the temperature of the gas mixture from the SMR to 370 degrees Celsius. Next, the mixture will undergo water gas shift reaction at 370 degrees Celsius and 12 atm at the WGS reactor. Here, carbon dioxide and hydrogen are produced while carbon monoxide is shifted with steam to produce additional hydrogen and carbon dioxide, and the reaction is exothermic. The first strategy to increase the selectivity and yield of hydrogen in the SMR reaction is by increasing the inlet temperature of feed stream at the SMR reactor. This is because endothermic reaction favors high operating temperature in order for the reaction to shift to the right. Next, decrease the inlet temperature of the feed stream at the WGS reactor. This is because exothermic reaction favors a lower operating temperature in order to shift the reaction to the right. And the third strategy to maximize the selectivity and yield of hydrogen is by increasing the concentration of methane in the feed stream of SMR reactor. When a species is added to a reaction, the reaction will favor the side opposing the addition of the species. Hence, by increasing the concentration of methane, the equilibrium of the reaction will shift to the right. Next, increase the concentration of steam in feed stream of good reactor. This is because when a species is added to a reaction, the reaction will favor the side opposing the addition of the species. And the last strategy to maximize the selectivity and yield of hydrogen is by decreasing the inlet pressure at the SMR reactor. This is because if the pressure in the system increases, the equilibrium will shift to favor the side of the reactor which involves less mole of gas. And from the chemical reaction equation at the SMR, the product side have less mole of gas compared to the reactant side. Hence, the equilibrium of the reaction will shift to the right. Here is the stoichiometric model for the SMR reactor, which will help us to determine the values that will be used in our calculation later. Based on reference, we know that the ratio of CH4 and H2O at the feed stream is 1 to 3. Hence, we assume the fraction of CH4 as 0.25 and H2O as 0.75. And the conversion for the reaction is assumed as 95%. Then, the change in the reactants are determined, as well as the delta. In this calculation, the expansion factor is considered since it is a gas-phase reaction. For the rate law calculation, the first step is to determine the partial pressure of each component by assuming the partial pressure of methane. Here, we assume the partial pressure of methane as 3 bar and the partial pressure of other components are then calculated using the relation based on reference. And the value of partial pressure calculated are shown here. Next, we calculate the rate constant and equilibrium constant based on the formula we obtained from the references. The calculation is shown here for rate constant and equilibrium constant. Next, the absorption constant for each component in the reaction is calculated based on the respective formula for each component as shown here. The equation shown here is obtained based on references. Next, the DEM for the reaction is calculated where DEM is equal to 1 plus KCO PCO plus KH2 PH2 plus KCH4 PCH4 plus KH2O PH2O over PH2. Then, after we obtain the DEM, we will proceed to calculate the rate law using the formula shown here, and the value of rate law obtained is shown here as well. The equation used to calculate the weight of catalyst is derived based on the general mole balance equation. Hence, we obtain the weight of catalyst used in this reaction is 109.93 kg of nickel oxide. The volume of SMR reactor is calculated by using the space velocity of the reaction. Here, the equation is space velocity is equal to volumetric flow rate over volume of reactor. First, we calculate the volumetric flow rate of the feed using the formula FA0 over CA0 and we obtain the volumetric flow rate as 7612.388 meter cube per hour. Then we substitute the value into the space velocity formula. Here, the space velocity value is 11,600 per hour and it is obtained from a volume of the SMR reactor obtained is 0.6564 meter cube. For the WGS reactor, the same step is applied as the SMR reactor to calculate the volume. The values such as flow rates, temperature, and pressure are substituted accordingly. Finally, the overall selectivity and yield of H2 is calculated. The selectivity obtained is 3.158. Next, for the overall yield, the yield obtained is 3.
Let's discuss the process modeling and simulation part of the project. From the requirements, the project includes the result from using the simulation software, which is Symmetry, the result coming from manual calculation and also the reaction engineering one, and finally the result from ranging the temperature of the feed, the pressure of the feed, and the molar flow rate of the feed on the overall reactor performance. So the image you can see below is the process flow diagram we used in the simulation software in Symmetry. We included one mixer, two packed reactors, which is one the SMR reactor and two the WGS reactor, and we also included two condensers in the process flow diagram. So the first step for the manual calculation is to develop the general mole balance equation for each of the component. After that, we can easily take out any constant in the equation. For this, we can assume that the volume is constant, and since the volume for the reactants are the volume of a cylinder, we can easily replace that into the equation as well. For the steam methane reformer reactor, we can easily see the result from the Symmetry simulation and also the manual calculation. The result from the manual calculation are based on the reaction engineering 1 chapter of the project, and we can see that the deviation error is big between the two values. Similarly, for the water gas shift reactor, we have received the result from the Symmetry simulation and also the manual calculation from the reaction engineering 1 chapter. And similarly, the deviation error between these two values are also large. And now, to discuss the explanation for the deviation error between the two values, we can see that there is a large difference between the volume used in the Symmetry software, which is 0.133, and also the volume obtained from the manual calculation in the reaction engineering, which is a 0.656 for the SMR and 1.605 in the WGS. Now, this volume of the reactors are very related to the space velocity, in which it is also related to the initial volumetric flow rate for each component. Now, as the volume of the reactors decrease, we can expect that the volume for the initial volumetric flow rate for each component should decrease as well, making it more feasible for that reactor.
For the next part of this chapter, we will conducting sensitive analysis using the case study function for Symmetry. The objective is to investigate the effect of temperature, pressure, flow rate, and composition on reactor performance. In order to do so, we need to define the reactor performance. In this report, the reactor performance will be determined by the production of hydrogen. For each case, the mole fraction and mass flow rate of hydrogen were selected as the dependent variables. Meanwhile, temperature, pressure, flow rate, and composition of methane feed will be selected as the independent variable. The case study will be conducted as summarized in the table. The first case is the effect of temperature. According to the graph, production of hydrogen in both SMR and WGS reactor increases as the inlet temperature of methane feed increases. The increase in methane feed temperature caused the inlet stream of SMR to increase, which also increases the temperature inside of the reactor. According to Arrhenius equation, rate constant is temperature dependence. Rate constant increases as the temperature of the system increases. Since rate constant is directly proportional to rate of reaction based on Rate law equation, the rate of reaction inside the SMR will increase as the temperature of the reactor increases, which results in increase in production of hydrogen. Therefore, explain the increase in mole fraction and mass flow rate of hydrogen. The increase in rate of reaction in SMR also increases the production of carbon monoxide. Since carbon monoxide is the base component for the reaction inside WGS reactor, the increase in production of carbon monoxide causes the concentration of carbon monoxide supplied to the reactor to increase. According to Rate law, concentration is directly proportional to rate of reaction. Thus, the rate of reaction inside the WGS reactor increases, which leads to more production of hydrogen. The second case will study the effect of pressure. Both graphs below shows that the production of hydrogen in both SMR and WGS reactor increases as the inlet pressure of methane feed increase. However, at a certain value of pressure, the production starts to slightly decreases. The increase in pressure of methane feed can cause the pressure inside the SMR reactor to increase. As the pressure of the reactor increases, the reactor inside the reactor are compressed, causing the space between the particles to decrease. Due to the confined spaces, the collision between the particles will become more frequent, thus increase the chance of effective collision and lead to increase in rate of reaction in the SMR. The particles also collide with the catalyst more frequent, which also lead to increase in rate of reaction in the SMR. The production of hydrogen will increase, thus the mole fraction and mass flow rate of the hydrogen will increase. Meanwhile, there are also an increase in production of carbon monoxide, which lead to an increase in rate of reaction in WGS reactor. The hydrogen production will increase, thus the mole fraction and mass flow rate of hydrogen inside WGS reactor increase. As the pressure of methane feed keep increasing, the mole fraction and mass flow rate start to decrease. The drop in production of hydrogen is due to the fact that steam methane reforming reaction favor in lower pressure. The production begin to drop as the pressure exceeds 2,900 kPa. According to Liu, the usual range of pressure that was applied in reforming plant is in between 2,000 to 400 kPa, which explains the slightly drop in production of hydrogen in both reactors as the pressure begin to exceed more than 2,900 kPa. The next case is the effect of flow rate on the production of hydrogen. The graph shows that as the molar flow rate of methane feed increases, the production of hydrogen in both reactors decreases. There are two possibilities that could lead to the result as shown. The first one is as molar flow rate of methane increases, the velocity of the methane supplied to the reactor increases. The methane resides in the reactor at a short period of time. Thus, the reaction time is too short to allow for a complete conversion. The conversion of methane will decrease, which means the production of hydrogen is also decreases. The second scenario shows that the increase in molar flow rate causes the temperature of the SMR inlet stream to decrease, which leads to decrease in rate of reaction as the temperature of the reactor decreases. The reason behind the occurrence probably due to methane have a low specific heat capacity. The temperature of inlet SMR is the result of the thermal equilibrium between the methane and steam. The only thing ever affecting the thermal equilibrium is energy provided to the system from any sources. The amount of heat transfer, delta Q, is proportional to the heat capacity of the object. Thus, small specific heat capacity results in small amount of heat transfer. The system able to reach the thermal equilibrium at a very small temperature. Moreover, concentration can affect the value of specific heat capacity as well. The increase in molar flow rate causes the concentration of methane to increase, thus decrease its specific heat capacity. Therefore, the heat transfer decrease and temperature at which the system achieves the thermal equilibrium is much smaller. The final case is the effect of composition on the reactor performance. Both graphs show that as the mole fraction of methane increases, there will be an increases in production of hydrogen. However, after a certain composition, the production of hydrogen begin to decreases. As the mole fraction of methane increase from 0.1 to 0.3, the concentration of methane in inlet stream of SMR increases. Thus, the rate of reaction inside the SMR increase, which also increases the production of hydrogen. Therefore, the mole fraction and mass flow rate of hydrogen increases. However, as the mole fraction of methane increases from 0.3 to 1, the system begins to counteract by decreasing the mole fraction of steam. Therefore, the reactant for the reaction is insufficient. Due to insufficient reactant, the rate of reaction begins to decrease, thus the production of hydrogen also decreases, which is why the mole fraction and mass flow rate begin to decrease.
Hello everyone, my name is Emily Lee Ming Xuan with the student ID 19001609. So for today, we are going to discuss about the part for separation process 2. In the introduction, we have introduced on the hydrogen, which is the most abundant element in the universe. Due to its sustainable properties such as clean and minimal carbon emission, hydrogen has been proposed as the ultimate energy as a renewable fuel in this century. Next, we can also refer to the hydrogen, which may be produced from a wide range of sources, including natural gas. Steam methane reforming, which also known as SMR, will be combined together with a pressure swing absorption system that is most common gas separation technique used for hydrogen purification. Therefore, by understanding the adsorption process and also by designing a purification unit with the best performance, we require the information from CEB 2063 Separation Process 2. Next, I would like to brief you on the selection for the hydrogen enrichment unit. So, the hydrogen enrichment unit that we are going to select will be the pressure swing adsorption, which is known as the PSA technology. The reason that we choose the PSA is because we can extract the hydrogen from the synthetic gas under high pressure. Compared to another two types of cyclic adsorption process, which are vacuum swing adsorption (VSA) and as well as the temperature swing adsorption (TSA). The PSA process has better performance in obtaining high hydrogen purity from a hydrogen-rich gas stream. According to our research, PSA was the first developed technology based on the Spectrum cycle that required two fixed adsorption beds to preferentially absorb one component from the feed mixture. Furthermore, PSA system is an ideal separation method due to its ease of application over a relatively large range of temperature and as well as the pressure setting. For your information, adsorbent play a significant role in the adsorption process, and the selection will be determine the performance of the separation unit. In the separations of multi-component gas mixture, two adsorbents are chosen as single adsorbent is difficult to purify hydrogen due to the presence of several impurities in the mixture. Therefore, activated carbon and Jolrite 5A are selected as adsorbent due to the high porosity and selectivity. In addition, the second adsorbent that we have chosen will be the Jolrite 5A. And the Langmuir-Freundlich load, by referring the loading ratio correlation, we can know that it's suitable to compute adsorption energy distribution onto the adsorbent surface that is heterogeneous. With the model formula of Q1 equal to K1 plus K2 T bracket multiplied by K3 exponent KQ over T by the power of Pi, as well as using the overall formula with the denominator below and also the numerator, and we can calculate that the LRC model against adsorption of gas on the activated carbon and Jolrite 5A were constructed.
The first strategy is to increase the equalization time while decrease the pressure equalization step. This is because the contaminant in the feed gas must be thoroughly absorbed before pure H2 can be created through the product end. The second strategy is to shorten the adsorption time. This is because the presence of contaminants increases throughout the adsorption process. CO2 will be entirely trapped in the activated carbon bed in a shorter absorption time. The third strategy is to lower the feed flow rate. As the input flow rate rises, the amount of time synthetic gas spent in the absorbent bed decreases, which means the syngas does not have enough time to touch the absorbent, resulting in reduction of H2 purity. The fourth strategy is to increase the purge to feed ratio. Higher purity purge gas, as the purge ratio rises, allow more pollutant to be desorbed and flowing out with the purge gas. Desorption occurs in third phase for 2-bed 6-step PSA unit, which also known as the concurrent depressurization or blown down. Therefore, desorption can be completed by lowering the PSA system pressure. Thank you.
Now for the group reflection. First of all, we needed to design a steam methane reforming plant for the production of 30,000 tons H2 per year with 99.99% purity. And during the project, we felt confused of the problem statement and lack of knowledge on the SMR plant. And after a few discussions, all the discussions on each chapter was clarified. And as an evaluation, the team members communicate with each other constantly on the project, and we also checked up on others' works regularly and always asked to clear confusion. As an analysis, the team members can find the solutions to the task given for each chapter, and the obstacles during the project, we can see that there is a lack of knowledge in the topic during the first phase, and making it very hard for us to start a project. And overcoming the obstacles, we read the provided articles in the problem statement, and for the progress report, it really helped with starting the whole project. And as a conclusion, researching on the problem is very crucial to get an overview of the project, and for future projects, for future team works, we need a clear timeline within the group, and we need to always communicate with each other in case there is a confusion in any of the chapters.